Right. Now that we've spent some time looking at surface parameterizations and learning how to interpret them and create them, we can now actually use these parameterizations to help us integrate over surfaces that are not flat. So, if we think about the history of what we've done in this class, where we've been and where we're going, we can connect surface integrals to what we've done in chapter 15, specifically in chapter 15.1 and 2, or 15 and as well as in 15.4, which is where we did polar. So all the double integrals that we did in chapter 15, so let's go ahead and just write this at the very top here to kind of compare and contrast. In chapter 15, we did double integrals over portions of, let's say, flat surfaces, i.e. regions within a plane. So for instance, if we take like some plane here, maybe it's the xy plane. I mean, in chapter 15, it was the xy plane, but in principle, we could also do these in any flat surface. It doesn't have to be the xy plane. Literally, it just has to be flat, because you are always free to go ahead and place a coordinate system on a given plane, and then it's indistinguishable from the xy plane if you so choose to describe things in that way. So in chapter 15, regardless of how we think of this plane, essentially we are doing integrals over a flat space. So the actual space, it has zero curvature, but that doesn't mean our region was like, rectangular. This region definitely is not rectangular. Its boundary is curved, but the actual surface itself is not curved. So distinguish this from taking a piece of paper on a table and drawing some amorphous blob like I just did here, versus taking a sphere like a basketball and then drawing on the surface of the sphere something like a continent, for instance, on the globe. Such an example here of like a continent on a globe, despite the Earth looking flat close up, it is certainly not, and the surface is curved. Sorry, flat earthers. So these integrals were essentially, in chapter 15, the actual two-dimensional space was not curved. What we're going to be doing now is actually integrating over surfaces that are curved. So maybe integrating over the curved surface of a sphere, for instance. Something like that. So that's the main difference here. Chapter 15, we were integrating over surfaces that had zero curvature, and now we're integrating over a surface that has a non-zero curvature. Effectively, that's what this is. So, much like what we did with line integrals, if we start off with a very generically written integral, in this case it's a surface integral, so it's a double integral, the name of our surface is S, we're going to integrate a scalar function. So this is the first type of surface integral we're going to do. These are scalar surface integrals. We'll also have vector surface integrals in the next section. So much like with scalar line integrals, we take our scalar function that we're integrating, and we take the parameterization of the thing we're integrating over. So in 16.2 and 3, we were integrating over one-dimensional paths. So we had parameterizations of the form R of t, a parameterization with one parameter, so one variable. Here we have two variables, so this is parameterizing something that's two-dimensional, which in this class we call a surface. So we make the replacement, replace each x, y, and z in our scalar function with the x, y, and z components of our parameterization, r of uv. And then we are going to multiply with the magnitude of the cross product of our partial derivatives. What's really interesting here, what I think is interesting at least, is what this quantity does. Now, normally in a semester where things aren't as chaotic as this semester has been, we actually spend some time going over section 15.6 before we move into chapter 16. That was omitted this semester. But that section goes into a great depth of detail, a great amount of detail here on what this actually tells us. So I'm not going to make a whole video on that, but I will very briefly tell you effectively what this thing does. So from the big perspective of Calc 3, what we know from Chapter 15 up here is that we know how to integrate over surfaces that have zero curvature. Okay? Well, the thing about curvature is if you have an area, so whatever this area here is, if we are able to take our surface and let's say we actually like bend it a little bit, maybe it does something like, maybe that's our new surface. Maybe we somehow do some bending of this. So we imagine morphing this surface. And now what's going to happen here, this curve is also going to be bent in some way. It might be like elongated in another way, and maybe it's sort of like this. Who knows what this looks like after we bend and twist it? So maybe it turns into something like this. Maybe that's what it looks like now after we do this bending. So the area over here, so let's call this domain D. Okay. So we have some domain D, and then let's say we have some sort of way to take this and bend it and twist it. Let's call this our parameterization R. Okay, so there's two variables here, u and v. So essentially what we do is we take a point in this flat space, let's say some point uv, and then this function r takes it and maps it. Maybe this point ends up being right here. And this point here would be, let's say, I don't know, this would be r of u comma v. This domain is going to be different here. Let's call this actually S. So this area of S here, so the area of D is not necessarily, in general, it's not equal to the area of S. So if you take something and you try to stretch it and shrink it down, you're going to get different areas. It doesn't have to be shrunk, it could be stretched. Just think about the very real-world problem of projections. The first time you ever heard of a projection was before Calc 3, and it was when probably you were in a geography class in middle school, maybe high school, where you talked about different types of projections. The Mercator projection, I forget all the other ones, doesn't matter. But the idea of taking the Earth and mapping it into a single large rectangular representation. Different projection schemes, in other words, different functions Remember, we talked about there's an infinite number of ways to parameterize things. So you can think of the Mercator projection as one such function, one such choice of how to parameterize the Earth. Different parameterizations, and therefore different cartographic projections, will distort areas in different ways. Sometimes distances are preserved, but then the areas are skewed, or maybe angles are preserved, but distances are skewed. So just because you have a function that can turn one into the other doesn't mean that the areas between the two of them will be preserved. Depends on the surface. So in general, going from a flat surface to a curved surface, things like areas are not preserved. And since we're doing a double integral here, the actual area of the surface is pretty important here. So what this actually tells us right here, this magnitude of the cross product, this actually tells us locally to a point. So this point here, when it gets turned into this point here, you can think about zooming in really close to this point, zooming in like, you know, a billion. And then what you end up checking here is if we take a little square or rectangle surrounding the point and then we send it to our new space, that will turn into it will morph a little bit. So this tells us effectively what is the distortion factor. So this is called the Jacobian, but we can very informally think of it as area distortion factor. So if it's bigger than 1, then the areas are going to stretch. So if you have a smaller area in the flat space, when it goes to the curved space, it's going to get bigger. If, for instance, maybe this quantity is less than 1, like some number between 0 and 1, then it will shrink the area when we move to the new curved space. So you can think of this as a measurement of the extent to which the area surrounding that point stretches or shrinks. Okay. Lastly, before we move on to the next example and then in the next video, is the same result that we've had all along the semester. And that is whenever you do a certain type of integral of the function, the constant function with value 1, you get back something very important geometrically, something intrinsic to the surface over which you're integrating. So if you do the double integral over a surface S ds, so here I'm not writing it, but really the function is 1. I'm just taking this and I'm replacing it with a 1, but 1 ds is just ds. We don't need to write the 1 explicitly. This will give you the area of S, so the surface area. Well, if you happen to know that your surface S is parameterized by R of uv with some domain D, then you can further say that this is equal to, that's my very long equal sign, that's equal to this. It's the same replacement up here, but specifically applied to the case where this function is just equal to 1.